So let us see the Feistel structure. So this particular structure will be used for the modern cryptography. For example, your DES algorithm, data encryption standard. In that particular algorithms, we use these Feistel structures here. So before we go towards the DES algorithm, so let us see the a general structure of this given by Horst Feistels here. Okay. It is a structure used in most of the modern cryptography. Okay, modern cryptography, and this is designed by Horst Feistel. So after taking its name, we term it as the Feistel structure. Okay, so if you look at this particular diagram, first this all modern cryptography techniques will follow the block cipher. The block cipher technique means the plain text will be divided into blocks first. Okay, so it is depend upon algorithms. If you are using the DS algorithm, then the block size will be of 64 bits. If you are using the AS algorithms, it is of 128 bits. So this is a single block. So from that plain text, we have taken a particular block here. So you don't assume this one to be the only the plain text blocks here. We have so many n number of blocks, so this may be the a particular block here. Okay, a block here. So in that particular block, we just divide into equal parts here. Okay, this is for the encryption part. In encryption part here, we want from the plain text, we want to generate the ciphertext here. From the plain text, we want to generate the ciphertext, but in that plain text, we have already divided the plain text into blocks, and from that block we have taken the first block. After completion of this block, we will go for the second block. After completion of the second block, we will go for the third block, and so on up to the last n block here. So let us see how actually a particular block encryption works here by using the Feistel structure. So in that, a particular plain text block, so if it is of 64 bits, if it's 64 bits, then we will divide it into 32 bits, and also here 32 bits here equal parts. So L stands for the left side and R stands for the right side here. So we divide the two parts. So this is the left part and this is the right part here. And then if you look at this particular structure derivation, so when we in the next step, what actually we do, the right side of this particular block, we just shift to the left side here in the next round here. Okay, in the next step, this arrow mark denotes the shifting here, direct shifting. This particular block we just put and shift here. Okay, this we just copy and shift here. Okay, so next, but how we have already filled this left hand side, but we have not yet filled this right hand side here. So how actually we fill this right hand side? If you look at this particular structure, we perform some operations here. Okay, we perform some operations. This we call this one as the f functions here. Okay, we have a f function or round functions here. Okay, we have a round functions here. F functions or the round functions here. So this is input to F, and also the key K1 here, K1 is input to this particular F here. Suppose this is a box. Here we have to perform some operations here. In that, what are the inputs? The inputs are the right hand side and also the key here. Okay, means this particular size and this size must be equal there, otherwise we cannot perform the operations here. Inside this box may be the XOR operations here. Okay, maybe the XOR operations, then we perform the XOR operations with this and this one. So I'm just telling that this may be an XOR operation, but this can be a different operations also. Okay, different operations also. So maybe a simple addition or simple any kind of operations here, but the size of these two should be equal there. Okay, and that particular output from this round function, we perform the XOR operations with the left hand side here. With the left hand side, we perform the XOR operations with whom? With the output of this round functions here. Okay, after performing this operation, you will be getting one output, right? With that output, we have to perform the XOR operations here. That particular result we keep in the right hand side. So if you look at this particular step here, we have divided the left hand side and right hand side. In the next step, the right hand side is simply shifted to the left hand side for the next step, and the left hand side is performed an XOR operations with whom? With the output of the round functions. And what is inside round functions? Inside these round functions are the input of this right hand side and the given key here. And the thing is that the key size and the right hand side should be equal. If it is of 32-bit, this will be of 32 bits here. Similarly, we have to perform the XOR operation with left hand side. Again, this output, the size of this one should be of 32 bits here as an example. 32 bits, only then we perform the XOR operations. The output is a 32 bit and we can fill the right hand side here. So this particular step, what we discussed, this one is called a round 1 here. Okay, it's a round 1. So like this one, in a Feistel structure, there are n number of rounds here. Okay, there can be 16 number of rounds, there are 8 number of rounds, 10 number of rounds, and so on. So these are nothing but one round. Okay, these are nothing but one round here. In a particular round, there will be one function, we call it the round functions here. Okay, so similarly for the second round, if you look at the second round, this is the result from the first round here. Okay, so simply you just shift to the left hand side and then you perform the XOR operations with the round functions here. The only difference is that here we use the K1 as a key, here will be K2 as the key. So there will be some mechanism, that is generating these particular keys here. Okay, for example, there is a mechanism key box, for example, as a key or a key generator. This key generator will generate K1, again this will generate K2, again this will generate K16 and so on here. So there will be a particular algorithm to generate this K1, K2 and K16 here. So we'll discuss this kind of method in DS algorithm, how in a DS algorithm these sub keys are generated from the main key here. A particular main key will be given, and that from the particular main key, these sub keys will be generated. Okay, these sub keys will be generated, and the size of this one we have to check in order to perform so that they could perform the operations here. Otherwise, if the size of K1 and RE0 are different, then we cannot perform the operations here. Again, if the result of this one of the round function is different, the number of bits is different from that of the left hand side, then we cannot also perform the XOR operations here. So we must check in order to have the same number of bits here. So like this one, you must follow it's in every round. So at the 16th round here, at the 16th, we also follow at the 15th round. At the 16th round, we got the result here. Okay, we got the result LE16 and RE16, but we cannot keep this as a result here. We swap the values. Okay, this right hand side we do not follow any round here. Instead of after getting the result in the last 16th round, that particular result, when I want to write the ciphertext, I just swap the values here. Okay, I just swap the values, and then this particular values become this one, the left hand side, this whole values are nothing but from the right hand side, and this right hand side, the whole values are nothing from the left hand side here. We just swap the values, and then this is the ciphertext here. Okay, ciphertext here. So similarly, if you want to perform the decryption part, it will be bottom up approach here. This is the top to bottom approach, this is the bottom up approach here. We have to perform the operations here. See, I have written RE for right hand side of the encryption here. LD means the left hand side of the decryptions here. Okay, and this is the right hand side of the decryptions here. So you just check how actually we put this one from this particular result. From this particular result, we make the inputs here. Okay, we made the inputs here, and then we start with K16, K15 up to K1 here. Okay, K1, this K16 is similar key that we use for the encryptions here. This K15 is also the similar key that is used for the encryptions here. So once the major parent key have generated the sub key, that particular subkey will be used in encryption as well as in the decryption method here. But the only thing is that they will follow, encryption methods will follow the top to bottom approach, and the decryption method will follow the bottom up approach here. Okay, so similarly you can just check this one. It's the same methods here. We perform the XOR operations, we perform the F functions here, and then we just swap the values. Okay, so the values until and unless we come to the key K1, this is the round 1 here. Okay, and until we come to the round 1, we just perform up to the round 1 here. Once we get the results, since we have swapped at the last part, you have to swap the results to get the plain text here. Okay, up to this one is just the reverse part. After getting the result here, you just swap the values like we did in the encryption part at the 16th round. Here at the first round, when you get at the topmost first round here, you just swap the values. That values will give you the plain text here. Okay, this is how a Feistel structure works here. Okay, you can just go through this one. You also have also written the notes, also given the formulas, how actually we swap the values, how actually we interchange the values, how actually we make equal values here. Everything I have written, you just check and you just try to understand what is the Feistel structure here.